Good morning. The last 16 or 17 lectures we have been discussing electrostatics, and today we are going to start with a new topic which is magnetostatics. So, let me put down what we have already learnt and let us look at what is going to change. So, we learnt that if you put a charge or if you put two charges at a distance, that a force is exerted which goes as q1 q2 over 4 pi epsilon naught 1 over mod r1 minus r2 cube times r1 minus r2, and this is the force, I call it F12 on a charge q1 due to a charge q2. So, this is, you have to draw the line q r1 minus r2. So, it is pointing towards r1 and the force is in this direction. From this force, which was experimentally measured, this is the Coulomb's law, we obtained the concept of electric field, and we define that as sum on I qi over 4 pi epsilon naught r minus ri over mod r minus ri cubed. That is, you have a whole lot of charges q1, q2, q3 up to qn. Each of those charges is at a location ri, r1, r2 up to rn. Then the electric field at any general point r is given by the summation of Coulomb's law for a unit charge placed at point r. From this electric field, we came up with a potential phi, which was, you can also write this as an integral. So, I will write this potential form as an integral 1 over 4 pi epsilon naught rho of r prime dv prime over r minus r prime. Given these things, we also derived some relations. First thing we found was the force on a charge is equal to the value of the charge times the electric field. That comes because Coulomb's law and the definition of electric field differ by only the value of the charge placed at r. We had that the electric field was equal to minus the gradient of potential. We also derived something else. We derived that the divergence of E was equal to charge density divided by epsilon naught. And there is another form of this, which was, we do the surface integral over a closed surface of E dot ds, it was equal to q enclosed over epsilon naught. Now, one of the things that came out of defining a potential was something very important. We proved that if you take any position r1 and any position r2, for any r1 and r2, if you did integral E dot dl, it was equal to a function of r1 and r2 only. So, it was some function, call it some f of r1 comma r2. So, you could then do integral r2 to r1 E dot dl, which was nothing but minus r1 to r2 along the same route E dot dl. That is because if you have an electric field that is in some general direction and this is your dl, E dot dl is magnitude of E magnitude of dl times cosine of this angle. But if dl change sign, it is pointing that way. Now the dot product is the same magnitude, but cosine of 180 degrees minus theta is minus cos theta. So the sign alone changes. So that is why there is a minus sign, is equal to minus some f of r1 r2. So if I take any closed loop, this is my r1, this is my r2. If I go this route and then I come back on this route, that is like doing r1 to r2 plus r2 to r1. But effectively if I do both of these, I am going around a loop. And what does it say? It says if I go on any loop, E dot dl, it is equal to f minus f, which is 0. This is an extremely important result, that in electrostatics the electric field can be derived from a potential, and equally this fact came from the fact that if you take any closed loop and integrate electric field around that closed loop, you will get 0. These two imply each other. It is clear that if this is true, then this is true, but equally true is the other way around, because if this is not 0, then I can find a loop where this is not 0, I take 2 points on it, then this integral is not equal to this integral, which in turn means E dot dl from r1 to r2 is dependent on how I went there, how I got there, which means I cannot define E equals minus gradient of potential. So these two statements are saying the same thing. However, this is a very important statement, and its importance comes most because we are going to break it now. Once we introduce the magnetic field, we will start finding that loop integral E dot dl is no longer 0. So it is very important to understand that this was for electrostatics, and it is equally important to know why it fails and to find out under what conditions it will hold and what conditions it will not hold. Okay, so we have a set of phenomena. We have charges, the charges exert forces on each other, the charges are cause fields, from the fields we can obtain back the charges, and if the charges stay put, we know that we can derive a potential, and that potential is a function only of the end points of my integral E dot dl. So it is a complete theory. Why do we need anything else? This is explained very nicely in Feynman, and I recommend all of you to go and read the introductory chapter of Robert Feynman's book Lectures on Physics, the second volume. But what the truth is, electrostatics is not a complete theory, and let us see why it is not a complete theory. Now we have all these equations, and I am going to now take a thought problem. I have got a wire, I will call it wire 1, I have got another wire, this is wire 2, and in each of these wires I am going to drive a current I. All right. Now you know that wires are made up of atoms, and if they are metals, then what is really happening is some of the electrons in the atoms, in fact some of the electrons in each atom, you have an overlap region of the valence band and the conduction band. So there will be electrons here which will be free to move to other locations which are allowed by quantum mechanics. So, the electrons start jumping from atom to atom to atom, and that is why metals are good conductors. So, we have fixed atoms which are positive in charge and moving electrons which are negative in charge. But there are as many electrons as there are atoms. We will assume 1 electron per atom is free to move. So, we have as many electrons as atoms. So, there is no net charge. So, there are n atoms with positive charge plus n atoms with negative charge, n electrons with negative charge. So, there is no net charge. If there is no net charge, then the electric field, which is 1 over 4 pi epsilon naught volume integral rho of r prime dv prime over r minus r prime cubed times r minus r prime. So, this expression, it depends on rho. If there is no charge anywhere, there is no electric field. So, these two wires in this picture should not exert any force on each other, because at every point there is no charge. The electrons may be moving, but that does not cause any force on between these wires. However, this picture is not correct. This picture is not correct because Einstein came along and he introduced the theory of relativity. And when he introduced the theory of relativity, something went wrong. This is not how it happened in history, but this is the best way of understanding what is going on here. According to Einstein, when an object is moving very fast with a velocity v, then the size of that object, let us call it L, this size reduces. So, this size becomes smaller. By how much does L become smaller? Well, L becomes L over L naught. The amount by which L becomes smaller goes like is a function of V over C. Actually, it is a function of V squared over C squared 1 minus. So, if V is very small, L is equal to L naught, but if V starts approaching C, then L becomes tiny. How does that affect us here? Well, if you look at say 1 ampere of current flowing through a wire, let us say the wire has 1 millimeter squared area, then we are talking about 100 amperes per centimeter squared, because 10 millimeters make a centimeter. So, 100 millimeters squared will be 1 centimeter squared. You have around say 10 to the 22 electrons per centimeter cubed, because that is like Avogadro's number if you had them all packed very closely, but atoms are heavy, they are further apart. So, around 10 to the 22 electrons per centimeter cubed is what you have. So, you need 10 to the 22 electrons multiplied by the charge of an electron, which is 1.6 into 10 to the minus 19 coulombs. This is the charge per cc into the velocity, we do not know what that velocity is equal to 100 amperes. If you put in these numbers, you will get that V is equal to 100 amperes divided by 10 to the 22. So, 1.6 into 10 to the minus into 10 to the 3 centimeters per second. So, V is of somewhat less than a millimeter per second. It is a very small number, and this is probably an overestimate of that number as well. So, V is very, very tiny. In fact, V over C is of the order of 10 to the minus. So, this is 10 to the minus 3, 10 to the 8. So, 10 to the minus 11, 10 to the minus 12 is the range of what V over C is. V squared over C squared is of the order of 10 to the minus 24. So, it is a very tiny change in length. So, if this was 1 meter, this length became 1 meter less 10 to the minus 24 meters. So, it is such a tiny change, you would not expect it to have any effect. However, it does. What happens is that if you look at the electrons that are moving, they have got squeezed slightly by this factor of 10 to the minus 24. But the ions, the atoms are not moving, fixed atoms. Because they are fixed atoms, they do not compress. So, the result is what I had written earlier, n times E plus n times minus E, which is equal to 0. This n is number of atoms per centimeter cubed. Well, this number is not equal to this number, because a centimeter has changed. Centimeter has become less by 10 to the minus 24. So, this number is slightly larger. Number of electrons because it 1 centimeter plus 10 to the minus 24 centimeters has now got contracted to 1 centimeter. So, a few more electrons are inside this centimeter cubed. The result, there is net negative charge. So, as soon as this current starts flowing, electrons are moving. So, because of the theory of relativity, electrons are squeezed a little bit. There are more electrons per unit length than there are atoms. So, there is negative charge. It is very tiny. You can imagine how tiny it is. We are talking about 1 part in 10 to the 24. Now, the same thing is happening here. All right. So, you have electrons and atoms, and the electrons are moving. So, they also get contracted. So, what happens if you look at it from the point of view of the atoms that are here? The atoms are positive. The atoms are not affected by the electrons that are moving in their own wire, because there are as many electrons this side as there are this side. So, there is no net force on atoms on this wire due to electrons in the same wire. But these atoms see more electrons here than atoms here. So, there is a net attractive force. Look at it from the point of view of the electrons. The electrons do not get affected by the atoms here, because as far as the electrons are concerned, the atoms are moving in the opposite direction, but there are as many of them there as there are here. For the electrons, these electrons are still, they are stationary, but the atoms are moving backwards. You should think of it as electrons are climbed into a car and are moving. So, both these cars are moving with equal speed. So, if you are inside this car, the other car is stationary, but the road is moving backwards. So, the electrons do not see standard number of electrons here, but they see the atoms are compressed. There is an excess of atoms compared to electrons. This is positive, and so there is attractive force. Result, due to Coulomb's law, these two wires start pulling each other. So, the conclusion, which you can prove rigorously, is Coulomb's law plus relativity equals force between neutral objects carrying current. It's very important. We have only used Coulomb's law. We have not used any further law of electromagnetics. But if you take Coulomb's law and you simply add the fact that moving things, according to Einstein, get shorter. If you just take that piece of information, you immediately conclude that current carrying objects attract each other. Now, once you have this idea, the question is, why can't we just use Coulomb's law and go ahead with it? And the answer is, you can. In fact, that is exactly what the theory of relativity does. The theory of relativity does not have electric and magnetic fields, it has only electric fields. But that electric field, representing it in a way that relativity finds it useful, is a very complicated business. The mathematics of relativity is not simple. But if you actually worked with Einstein's theory of relativity, you do not have an electric field and a magnetic field, you have only electric fields. And the theory is at a conceptual level very simple. However, the mathematics is difficult. The result is that when you come down to using it in simple cases, we tend to break up Coulomb's law into two pieces. Coulomb's law when things are stationary and there is net charge, that is our normal Coulomb's law. And Coulomb's law when there is no charge, but there is moving particles. And for that second case, where relativity tells us there is a force, we introduce a new concept. But you can see directly that if you have currents, there will be force between wires, and this was measured. Now, the way we do force calculations becomes complicated, because there is no charge here. So, I cannot put q divided by distance, I cannot do any of those kinds of actions. Furthermore, it is fairly clear that it is the velocity that is going to create a force, and even more, it is clear that it is going to be v squared. So, it is the square of the velocity that is going to give me a force. So, there we need to do some additional work to pull out such effects from what we have. So, what do we do? Well, historically what people have done came from another theory altogether. From way back, they knew that there were certain objects, magnets, that tended to point in certain directions only. If you took a string and you took a magnetized object and you waited for it to settle down, it would always point in the north-south direction. After a fair amount of time, people realized that this is because the earth itself is a gigantic magnet. This is the direction on which the earth spins, and this is the magnetic axis coming out somewhere in Greenland, and down here I suppose south of Australia. The strange thing that you should always be aware of is that at Greenland is the south pole of the earth, and near Antarctica is the north pole of the earth. If you put anywhere, say in India, the south pole of the compass wants to point towards the north pole. So, it will turn round till it points towards the north pole of earth. The north pole of the compass will try to point towards the south pole of the earth. This experiment people had done. They brought two magnets and they could identify which was the north and which was the south pole of each magnet. They found that if you brought two north poles close to each other, then there was a force between them which was repelling. Whereas if we brought a north pole and a south pole near, then the force was attracting. And it was also known that this force was inverse square law. It was just like Coulomb's law. In fact, if you took only the force on a pole of a magnet and you asked what is the force on that pole, you found that the force went exactly like the strength of that pole, let us say I will call it Q magnetic, times the normalization number divided by r square, and the direction of the force was in fact having to do with the direction of the magnetic field. This was seen, this was known, and once they thought about it, they said, supposing you take a magnet, a bar magnet, call it north, south, and you take lots and lots of iron filings. You have done this experiment in school. They found that the iron filings tended to arrange themselves in a pattern. So, all this was known, but now having done Coulomb's law, we know something else. We know that if you take a positive charge q and a negative charge q and you work out the electric field due to this, electric field looks like this. In fact, it looks exactly like the way the iron filings arrange themselves due to a permanent magnet. The electric dipole, this is a dipole because you have a charge and a negative charge. The electric dipole and the magnet are identical. The effect of the electric field created by an electric dipole and the pattern created by a magnet were the same. So, there is a clear parallel between whatever happens in Coulomb's law and whatever is being seen with magnets. And this was the state of things maybe around the beginning of the 19th century. So, they knew a lot about magnets. Magnets were used in practice because ships required magnets to navigate. They knew quite a bit about electricity because that had become a very practical subject, but they could not combine the two. That was where it was until people started studying current in wires, and they did something interesting. What they did was they took a wire, they drew a current through it, and then they took a permanent magnet with a north and a south and they brought it near this wire. Now, they already knew that there was something called a magnetic field defined by the magnetic field of the earth, because they knew that the earth is probably a dipole magnet. So, you can draw magnetic field lines. Of course, earth's north pole is in the south. So, you had magnetic field lines, and it was believed that the compass that we have was aligning with magnetic fields. Now, what they found was when you brought a magnet close to a wire carrying current, the magnet did not align itself with the earth anymore. It started aligning itself with the wire, or rather it started aligning itself along circular lines around the wire. So, if you look at these two pictures, you can see that the same thing seems to be happening. If you bring the magnet to different points, it is pointing in different directions. You take it far away from this wire, it starts pointing to the north again. So, the conclusion was there is something called a magnetic field. They gave it a name B, and the same magnetic field that the earth produces, a current carrying wire also produces it, because the magnet responded to both. Magnet responded to the earth by pointing towards the south pole of the earth. The magnet is also responding to a wire. So, there is magnetic field being produced by the wire as well. And then they did many more experiments, because they wanted to understand exactly what is the nature of this magnetic field that is produced by currents, because currents they knew by then, they knew how to produce currents, and if you could produce magnetic field using currents, suddenly the kinds of machines you could create became very interesting. So, they did a large number of experiments. I think that was a period when a lot of data was collected, and when they did all these experiments, they came up with a summary conclusion. They said that if you had a very tiny piece of wire carrying a current, it is not possible, but this is like, they did all these experiments and they said that this is the mathematical essence of what we have found. Take a small piece of wire whose length is dl, which is carrying current. Now, this dl has a direction, all right, and it is carrying a current I. And let us say you are standing here with a compass. So, this is R. This, in the notation that we have been using, is R prime. I always use R for where the scientist is standing or his scientist instrument is standing, and R prime is where the source, either the charge or the current, is placed. So, this arrow going from the current element to where my measurement, my magnet is standing, is R minus R prime. That is because R prime plus this distance is equal to R. So, if I just shift things around, this distance is R minus R prime. The magnetic field produced here, because it is a small piece of wire, it is a small amount of magnetic field. The formula was the small amount of magnetic field produced is equal to a normalization constant times I dl, the current times the length, cross R minus R prime divided by mod R minus R prime cubed. So, it is this length, this direction cross this direction. So, in this case going into the board divided by q. Now, if I keep only the direction and drop the magnitude, I can write this as normalization constant I dl cross R minus R prime unit vector divided by R minus R prime squared. So, this should be seen as very similar to Coulomb's law, because if I wrote dE, it would be normalization constant q times R minus R prime divided by mod R minus R prime cubed. And again, if I took the unit vector, this cubed will become square, and dE, this would be dq. So, it is the same kind of object, and we know it should be the same kind of object because we have already looked at it. This magnetic force and this magnetic field is nothing more than Coulomb's law and relativity. That is all it is. The fact that moving particles get squeezed and therefore a slight amount of charge is produced, so slight that you cannot measure the charge itself. It is such a tiny change, 1 part in 10 to the 24, no instrument can measure that. But 1 part in 10 to the 4 has an effect. That effect is what we are calling the magnetic force, the magnetic field. Now, if you have been alert, you will have a question at this point. The question is, we cannot create machines that are so accurate in shape, in size, that we can measure 10 to the minus 24. So, in that case, how is it that a factor of 10 to the minus 24 is observable? In other words, why does not it get washed out? Sometimes it is plus 10 to the minus 24, sometimes it is minus 10 to the minus 24, we will never see it. Well, I will have to take you back to the beginning of our courses. If you remember, I compared the strength of the electric force and the gravitational force, and I told you that the force due to electricity divided by the force due to gravitation was 10 to the power of 36. That is, if you take a proton, 2 protons, and look at the force due to electrical forces between them and take the force due to gravitation between them, there is a factor of 10 to the 36. The electrical force is 36 orders of magnitude stronger. If you took electrons, that is something like 10 to the 43. So, these are huge numbers. And I asked the question, why is it that we ever see gravitational force? The truth is, we only see gravitational force, we rarely see electrical force. And the answer was that these electrical forces come in 2 signs, positive and negative, and they adjust themselves so that they cancel perfectly. This cancellation is so good that 36 orders of magnitude are cancelled out within a few centimeters or within a centimeter, and anything beyond a centimeter or 2, it is gravitation that dominates and not electrical forces. So, if there is this good a cancellation that gravitation starts dominating, then clearly a force that is merely 10 to the minus 24 of electrical force is a very strong force. It is 12 orders of magnitude stronger than gravitation. And that is why, even though the magnetic field cannot be measured as a fluctuation in charge, its effect is extremely strong. And that is also why, if you look at the scale at which you observe phenomena, you see electrical effects, they are usually seen at very short scales, atomic scales, molecular scales. Maximum, you will start seeing them for a few millimeters. Okay, so, very small, less than millimeters. But if you start asking magnetic effects, the Earth's magnetic field is planetary dimensions. The Sun's magnetic field is even larger, and the galaxy has a magnetic field. The magnetic field has the scale which is of the order of the universe itself. There is a cosmic magnetic field. Gravitation is again the size of the universe. So, the difference is the electrical forces are extraordinarily strong, but they cancel extraordinarily well. The magnetic fields do not cancel that well, but they are very weak. So, on very short scales, the magnetic field does not really show up. But on longer scales, the magnetic field dominates over the electric field. But the magnetic field still has one problem. If you go to the equation, it says I dl cross r minus r prime. So, if dl changed sign or I changed sign, if you have positive and negative currents, then the net effect of the magnetic field is 0. So, just like you have positive and negative charges, you have positive and negative currents, but you only have positive mass. So, this is the reason why as you get to larger and larger scales, the magnetic field loses out to gravitation, because gravitation keeps building up. It builds up very slowly. It is after all 40 orders of magnitude weaker than everything else, but if you go 40 orders in size, then that is the only thing around, because every piece of mass pushes in the same direction, whereas the currents that drive a magnetic field tend to start cancelling, and the result that the magnetic field, even though it outlasts the electric field, you see it on larger scales, is much weaker than the gravitation. Okay. So, now we have this formula. Let me look at what this formula is saying. dB equals, now I am going to put in the mu naught over 4 pi. This is a normalization constant that comes out of SI units. I dl cross r minus r prime divided by r minus r prime cubed. Very complicated looking equation. So, let us see if we can use it and extract what this magnetic field really should be. So, I have a wire, and the wire is carrying current. I am assuming my wire has a very small radius a, negligible, and I want to know what the magnetic field is at some distance r from the center of the wire. Now, this wire is a straight long wire. So, clearly whatever magnetic field I calculate here, it will come from I dl here, it will come from I dl here. Let me take a piece that is a height z above and a height z below. If I join this current element to this observer's point, then you can see I cross r minus r prime, that direction. If I do the cross product, I have to use my right hand rule. That is, I take my right hand, point it into the board and try to screw a right hand screw starting from the first vector and going to the second vector. So, it gives me a value here. Now, if I do the same thing here, it also gives me the same value, except that in this case the value is greater than 90 degrees, in this case the value is less than 90 degrees. So, this is some theta, this is 180 minus theta, but both sine of theta is equal to sine of 180 minus theta. So, both of these give me the same force, and the force is into the board. So, I just take pairs of points, pairs of ideal, and keep going to the top and the bottom, and I will get some number going into the board. Now, if I choose a point slightly above, well, the same argument will hold, and since if the wire is long enough, I will get the same answer for the magnetic field. So, whatever answer I get for the magnetic field B, it is along the theta direction and it is a function of r. It is not a function of z, because if I moved slightly up, it does not make any change to my calculation, and it is not a function of theta, that is fairly obvious. So, B is into the board and is a function of r only. If I now try to calculate this number, let us see what I get. I have my wire, because it can be for any z, I am going to choose z equals 0. This is r, and I am taking a piece that is z above and z below. I know that the B is in the theta direction. So, all I need to do is calculate the magnitude. So, I get dB is equal to mu naught over 4 pi, the current I dl. The dl cross r minus r naught is just going to give me a sin theta divided by r minus r prime squared, where the theta I am talking about is this angle. That is, it is this dl divided by this, I mean the angle between this dl and this r minus r prime. This angle I want sin theta, so sin of 180 minus theta is the same sign for both of these, is r divided by hypotenuse. So, it is equal to mu naught over 4 pi I dl times r over square root of r squared plus z squared divided by the square of this distance, which is r squared plus z squared. So, the total magnetic field B is in the theta direction and is equal to mu naught over 4 pi I can pull this r out, times integral minus infinity to infinity dz divided by r squared plus z squared to the power of 3 halves. I am not very interested in what the answer is. We are going to find a better way of calculating the answer. What is more interesting is to understand that there is something called a magnetic field. We have identified it because if you put a magnet anywhere in this room, it will start pointing north. That same magnet tends to point in another direction, the theta direction, near a wire. So, I can calculate that B using this formula, and I can calculate it for any kind of wire, not just a straight wire. If you give me a loop, I can use the same calculation. But what use is this B? So, you need a second equation. You need an equation that gives me force given the magnetic field. And the answer for that was that if you calculate B, then the force due to that B is equal to Q V cross B. That is, if I have a magnetic field, it is in some general direction, and I have a charge Q, and the charge is moving with a velocity v, then I take that velocity, cross this magnetic field, and I will come out with a force F, which is q v cross b. And if you take many charges and have them all moving together, then this q v multiplied by n, this becomes j. So, the force is sometimes also written as force is equal to j cross b. That is, the current density across the magnetic field is the force per unit volume. This is current per unit area, and this comes just from the fact that QV cross B is the force on one charge. If I have n charges, it will be n times QV cross B, but NQV is nothing but current density, so you get J cross B. Now, it is very important to understand how this picture connects back to the original picture I brought. In the original picture, we had that the force was proportional to V squared over C squared, because V squared over C squared was the amount by which the length reduced, and therefore, that was a measure of the Coulomb force, and it was also proportional to 1 over d squared, the distance squared. Now, where did this V squared come from? Well, there is one V here, Q and V, so the V comes here, but there is another V here, because this magnetic field is due to current, right. Current is nothing but Q and V. So, there is one V here and there is another V here, so there is a V squared, which is the same V squared that we saw in the original picture. So, it is after all the same picture. The magnetic field force is the same picture that earlier we had. Supposing you had two wires carrying current, this current would cause a magnetic field. Magnetic field would be in this direction B, and then you would have a second force which would be the force J cross B, that would be a J cross B force, and the force would cause these two wires to attract each other. The same argument, if you use the Coulomb's law, you would say because of current the electrons are moving, electrons are compressed, so there is net negative charge, and because of that net negative charge the positive atoms here get attracted. Similarly, there is net negative charge here, the positive atoms here get attracted, and so there is a Coulomb attraction which is proportional to V squared, which is the same answer we are getting here. The 1 over d squared came from Coulomb's law, which is the same answer we are getting here as well. The picture I have given here is not the picture that is there in your textbook. In your textbook, he goes immediately into the Biot-Savart law. So, he immediately says dB is equal to IDL cross r minus r prime over r minus r prime cubed, and works out the consequences of that. Now, that is perfectly all right. I mean, from calculating things, that is the formula you need. However, it is a very unreasonable equation just to accept. It is saying that current is in one direction, the distance to the observer is in another direction, and the force in the magnetic field is in a third direction. Why should that be? And that is why I have brought these other ideas in. The magnetic field is not an independent field. The magnetic field is just another aspect of Coulomb's law. However, it is convenient for calculation, for mathematics, to treat it as another field. Whenever you introduce velocity into Coulomb's law, you are going to introduce magnetic field because of relativity, and because of relativity you are going to have V squared coming in, which is two currents. V implies a current and V squared will imply two currents. So, interacting currents give you magnetic force, and that is what we get here, interacting currents giving you a force of attraction. All these ideas we are going to make more precise in the next few lectures, and we will go back to following your textbook, but I at least do not find it very comfortable to just jump into formulas and start using them. So that is why I have introduced these concepts in this more roundabout way, so that you will feel that there is some reason why the magnetic field exists. Magnetic field isn't an independent force at all. The moment you set Coulomb's law, all the remaining equations of electromagnetics are pinned down. Just by adding relativity, all 4 equations of Maxwell are fixed. There is nothing new that can happen because of magnetic field. It is all implied by the electric field itself. And the reverse is true. If you wrote down the magnetic field equation and then use relativity, you can predict electrostatics. Okay.